doing cold welding. We were actually doing lots of topics, but it was sort of under the topic of cold welding. And I'd handed this thing around before. This has got aluminum bonded to steel. And the way they do this, they have before they stamp it into a part, they have a piece of steel coming in and they brush and clean the surface, basically just a big sanding machine basically, it cleans and roughens the surface of the steel. And then they have the aluminum, actually then the steel goes through a nickel plating bath, okay? So it gets a nice new nickel coating. And then they have some aluminum come off, another roll of aluminum about the same width, and it goes through a shot blast cleaning and some other things to roughen its surface. I guess sandblast cleaning before shot blast. Or shot blast, anyway, it's got a nice new clean surface. And then they bring these two sheets of material together under a lot of pressure on a roll, and they actually heat it up to about 400 or 500 degrees, so it's actually warm bonded, and they just smash the thing together, okay? It's called roll bonding, and it gives a reasonable strength joint. That's the way they make aluminum Babbitt bearings for engines. Piston engines, basically you got a piece of steel and you got the aluminum on there. It's the same machine that made that. Makes the roll of steel with the aluminum on it for the bearings for the crankshaft or connecting rods of the piston engine or whatever. So that's the cold bonding operation. There's also, I should have brought in something else, I forgot. There's lots of bimetallic strip joining that's done in the world. In fact, back in the early 1980s, they were closing down all the chromium plating lines in the country because people were learning that hexavalent chromium, CrO3, is a carcinogen. It's a fairly potent carcinogen. And they showed that people that worked in these chromium plating shops had a higher incidence of cancer than others. And so, because they didn't have good environmental controls, a lot of these shops shut down. And if you go look at an automobile from the 1970s, it turns out that it'll have a chrome-plated steel bumper. If you start looking at automobiles in the early 1980s, you'll see they had aluminum bumpers, which aren't much good, with little rubber strips, and then they started using plastic for bumpers in the later 80s. Well, what happened, and actually if you start looking in the early 90s, you start seeing the chrome-plated steel bumpers come back on cars. You haven't paid attention to all the bumpers on cars yet, have you? But if you start looking at the age of cars, you can see this transition in the 1980s. And that was because they shut down the chromium plating baths, and it was about 10 years before people figured out how to start them back up. They didn't shut down all chromium plating, but for heavy automotive production, they basically shut down the plating baths. Well, when they first did this in the automobiles, they still had the regular old car designs, had steel bumpers, and they needed a chromed bumper. And so it turns out in the early 80s, Texas Instruments down here in Attleboro, Massachusetts, was the Metals and Controls division. They were growing. Became $1 billion plant, and they were probably the biggest plant in Massachusetts. But they were predicting they were going to become a $5 billion business in a few years because they couldn't chrome plate bumpers. What they had to do, because it was already in the design to have in the cars, to have a chrome bumper, they basically were stainless steel coating steel. And so these guys down here, who are kind of the largest roll bonding people in the world, do cold welding of one metal on top of another. We're making all the bumpers for automobiles, or the material, the stainless steel clad bumpers. Well, those were expensive bumpers, and they eventually got those out in the next car designs in the early 80s. But turns out, does anyone know why Texas Instruments would own a company that clads two types of metals? No, it turns out originally Texas Instruments, Cecil Green, who graduated from MIT, class of 1923, went down, he was graduated in geology. The big tall building here, the green building, tallest building on campus, is the geology building. That's because Cecil Green, the founder of Texas Instruments was a geologist and a physicist. And he went down to the oil business in Texas, and he bought a little company called Texas Instruments that made instruments for the oil field. These are like pressure gauges and other types of gauges. And one of the things they use are bimetallic strips. Okay, inside the gauge, they use these bimetallic strips. In fact, somewhere in here, we should have a thermostat over there on the wall. There's probably a Texas Instruments or someone else's bimetallic strip in there, and as the bimetallic strip heats up, because of the difference in coefficient of expansion, it will contract or expand or will curl, and that way you basically have a temperature sensor, and that's basically what the temperature sensor is in one of those things over there. So anyway, Cecil Green purchased this little company called Texas Instruments that was making these little gauges, and they later built the place up here. It was in the 1950s, for some reason, they decided to get into the silicon business. And that actually sort of took over and became a huge business. So it turns out the bimetallics in this part of Texas Instruments was really because of their original business in making little instruments. But it's still a pretty good size business making clad metals of all kinds for people. Now it turns out if we want to look at what controls the strength of a ceramic joint, or no, of a cold rolled joint. Going the wrong way. Okay, sorry. This is in your handouts. But this is a plot of the oxide to metal hardness ratio. This was done back in the early 50s versus the percent deformation. So if I'm going to roll these two things together, the aluminum and the steel, or copper and nickel, or stainless steel and regular steel, I want to know how much deformation I have to get into the part before I get a decent bond. And it turns out that I guess I'll use it over here. If you look at the amount of deformation it takes with different metals in order to form a strong bond and plot it versus the oxide to metal hardness ratio, you find that various elements lie along here. And indium turns out to be the easiest material to cold bond. Indium is a very soft metal with a very high hardness oxide. And in fact, if you go use touchscreen displays at the ATM or something like that, that's actually got a layer of indium oxide on the surface. And it's slightly conductive or semiconductive. And so when you touch, there's an electrical signal there, and you're interrupting the capacitance of the signal. But it's an indium tin oxide that's on the surface. But indium is a very soft metal, very easy to deform itself, but the oxide is very hard. Aluminum is also relatively soft compared to some things like nickel alloys or steel or iron-based alloys with a very high hardness oxide. This is a relatively pure aluminum. This is aluminum alloy. If you go back and look at the individual data, here's tin and tin oxide, tin soft, and tin oxide is relatively hard. Most of the metals, steels and copper alloys and nickel alloys, more common alloys, it takes 80–90% deformation in order to get a good strong bond. But oops, why does that thing do that? I'm gonna have to. Does it have an auto? Oh, yeah, auto is off. Sorry. Okay. It also tends to overshoot. But anyway, okay. In any case, what happens, or the general explanation, is that if I have a metal, another metal, and I want to bond them, and I have an oxide on the surface, of course the oxide on the surface is all the way across the surface, but if I deform it, I'll break up the oxide as the amount of deformation tells me how much I've extended and stretched the surface. And if the oxide is very hard and doesn't stretch and deform, I get a lot of breaks in the oxide without, that gives me metal-metal contact across here without the oxide smearing out and recontaminating the surface. So it turns out that it's a fairly simple relationship here of oxide to metal hardness ratio versus the percent deformation to form a cold bond, but it works out very well. Indium with only about 10% deformation can give a relatively strong joint. And back when in the 50s and 60s, when they put 1 or 2 transistors inside a little metal can and they would seal it and you couldn't heat it up, they would actually make a cold bond by putting a little piece of indium in there and just squeezing that top can. This is an old, I don't have any of these because I remember seeing them when I was young, okay, but it's basically a top hat type of can or transistor with had some leads coming out of it, and this top cap, you had your semiconductor chip inside here, but this top cap got squeezed onto a metal base, and your semiconductor was inside here, and the whole thing was inside this can, and you would make your hermetic seal by just putting indium here and just squeezing the whole thing together, because indium was the easiest thing to cold bond. We don't use that as much, although the military is still using some of that stuff because they have to harden things for electromagnetic radiation, right? So they actually still use some of those technologies to encapsulate electronics inside metal cans. It turns out that this aluminum, I told you that for wire bonding, gold was the preferred material for making these wire bonds, but aluminum is number 2, is the only other thing that really seems to work. Gold works because it doesn't have an oxide to cause contamination. The aluminum works because it has a very hard oxide. Itself is relatively soft. And here's a picture, this is also from one of your handouts, of this kind of, I talked about the sewing machine that makes these wire bonds. So they have this thing called a sonotrode here, and the wire comes in and it squeezes the thing. You have this tool that squeezes it up against the wire bonding pad. You've got this is your semiconductor chip or your substrate that you're trying to bond to, and you've plated on some solder or some gold or whatever. It's typically gold to gold, or it can be aluminum to aluminum. And then you make the joint, and then the sewing machine kind of comes over, lifts over, presses down again, and then cuts it off and makes the wedge, what they call, in that case, a wedge bond. Page after this, I think, a similar picture of the gold wire coming in. This is on the semiconductor chip, but you actually have plated some gold on the chip, and you come down and you squeeze it. Sometimes they actually use a little hydrogen torch that melts a ball of gold that makes a button, and you squeeze the button on there. But a lot of times, most times actually nowadays, they're not using that much anymore. This comes out of this book by Tamala, Microelectronics Packaging. It's getting a little bit old. It's 1989, but he was at IBM, and it's a fairly comprehensive book if you want to look at kind of 1990 kind of technology for wire bonding and packaging and stuff. There's a more recent one, which I'm going to show you some stuff out of, reflow soldering, processes and troubleshooting. And this guy, I can't remember where he's from, but it's 2002. But I don't remember where he's from. But anyway, it's just 10 years more recent type of thing. So anyway, you make these thermocompression bonds, and these are the ones that something on the order of 10 trillion a year of those are made by cold welding. Which kind of leads us, since we're talking about electronics, into electronic packaging, where we use not just cold bonding, but we also use soldering. We're going to talk about soldering in more detail later, but for right now, this was a part of a roadmap by Toshiba Corporation that was put together to look at, in this case, they don't have an axis on here, but this is probably the number of inputs and outputs on a chip. Now, if I have a semiconductor chip, it turns out that The more transistors I put on there, the more inputs and outputs I have to have. So this is my piece of silicon, and I'm going to have a bunch of leads coming in to this. Typical size, you might know what the typical dimensions of a silicon chip are, although the G5 processors kind of shattered this, and a lot of the military electronics 10 years ago had shattered it. But typical Pentium and things like that, well, if you don't know, this was an original Pentium right there. In fact, that's the chip right there in the center, and it's about a centimeter on a side. Now, someone told me that the IBM G5 processor that's in the Macintosh is about an inch on a side. Well, the military was doing things an inch on a side back 1990, but only they could afford the loss rate. But now that we have 12-inch single crystal silicon wafers, people are going to larger chips. But the big problem with the larger chips is the coefficient of thermal expansion between the silicon and its substrate. I think I got something here. If I look at the integrated circuit has coefficient of thermal expansion of 2.6. The substrate will have, depending on whether it's aluminum nitride or copper or whatever, it can have a coefficient of thermal expansion of 6 to 27. And here are some other materials: glass, alumina, epoxy glass, polyester flex. Actually, 27 is polyester flex. So these are the different types of substrates that you might have that you're going to put your integrated circuit on. And the problem is these things heat up 30 degrees centigrade, or more and more. You don't want them to heat up more, but they might in some cases. So you've got a problem of coefficient of thermal expansion, and that just gets greater as the dimensions of the chip get larger. In fact, the Pentium 2, if I remember, was 2 chips. If you actually looked at the package, this goes back to 1995 or so. That was the Pentium. It was a single chip. The Pentium 2 was a chip that size, another chip about half that size, both in the same package, okay, right next to each other, because they couldn't make it any bigger because of these coefficient of thermal expansion problems of these things. So if you want, that one's got a dot on it. The little ink dot means it didn't pass test. But we'll talk about some of the rest of that later. So one of the techniques to make these is perimeter bonding. And before I get to perimeter bonding, I want to say something else. The number of IOs, which they call input-outputs, IOs, is proportional to the number of transistors. And there's something called Rent's rule. If you look in the beginning of this thing, it basically says that the number of transistors, or circuits, is proportional to the number of IOs raised to some, over a constant, raised to some other power, little n. And that power goes kind of as the square or so. But Rent's rule basically says the more transistors I put on a chip, the more complex it becomes, and the more inputs and outputs I have to interface with that thing. Now, eventually, at least I think, if you were to put everything onto a chip, if you could put everything onto a chip, then the number of IOs might go down. But we're still at a stage of design that tends to go up. And as you get to, the current Itanium is like 50 million transistors on a chip, or something like that. I think the G5 processor is something like 50 million transistors on the chip. And so those things are actually getting to the point where they need 400, 500, or 1,000 there's certainly plenty of a number of people who've designed chips, and they like to get to 1,000 or 1,500 inputs and outputs. Well, if you look at time here across the top, in 1980, we were down here with like 16 or 32 inputs and outputs with a dip. They call it a dip? Yeah. Dip. Here's a dip. It's an aluminum oxide. Actually, it's dark because it's about 94% aluminum oxide, and it's got about 6% manganese oxide. It's a ceramic, and if you could cut through this thing, you'd find the whole thing is metallized with gold layers or tungsten layers, typically tungsten, I guess. Tungsten layers, and you have this number of inputs and outputs along the side, right? So there's a chip carrier, kind of 1980 style. Then, as you come up here in 1985, you had what was called pin grid array, and a pin grid array was still a perimeter bonded chip, but you got the same aluminum oxide with the tungsten inside, but it comes out and it has a whole bunch of pins in an array, and so this one's got two rows, but I've seen them with 4 or 5 rows, but you can get up to, what's it say there, 400 or 500 if you get a big enough pin grid array. And that's typically if you open up your laptop computer, that's not your laptop, I'm sorry. If you open up your desktop computer and you start looking at what the chip looks like, it's going to be a great big chip like that, chip carrier like that, but it's got a little 1 centimeter chip in there, and all the rest of that space is just making the connections to it. So this is perimeter bonding, and the problem they had was wire bonding was good up through about 1980 or so, but for wire bonding, the closest approach you can get is about 7/1000 of an inch. Because remember, I got this sewing machine head that has to come down, and even though the wire is only 1/1000 of an inch, well, if I had 1/1000 of an inch wire separated by 1/1000 of an inch, although frankly that ball that I formed, that compression bond I formed, that's about 3/1000 of an inch wide. But if I only had 1/1000, if I had something, the ball that's 3/1000 of an inch wide, and a gap of another 1/1000, it would be 4/1000 on centers. But I can't get the head in there to do the mechanical joining if I've only got 1/1000 of an inch between the balls, so or the tips of these things. So it turns out about the closest you can go is 7/1000 of an inch. Well, if this is 1 centimeter, and I got 4 centimeters, and 4 centimeters is 1.6 inches, right? Since a centimeter is about 4/10 of an inch, divided by 0.007, and I get something on the order of about 250 wire bonds to that chip if I'm doing perimeter bonding. And that's a problem. Now, they did try some things where they would put a series of little square pads like this, and then they would put another row inside, and now all you had to do is make this wire bond, and then the next wire bond you make goes over the top of that one, right? And you might get up to 500, but you lost a lot of real estate for the semiconductors because you're using all this silicon for the pads, right? So you have a problem there with the with getting up much above 500 with wire bonding. So the next technology here is, well, a lot of these things are just kind of tab. Okay, 1995 tab. Actually, in 1990 I was working on tab or some of my students were working on tab for digital equipment when they existed, and they were going to go and compete with IBM and mainframe computers. Except mainframe computer use was going down like that because PC power was going up like this, and networking small computers and things like that. So DEC basically went under, but they were using tab bonding because they needed about 400 IOs, and I think there's about 380 some IOs on this particular tab tape, and they call it tab tape because there's one right there, but I can pass this one up to you guys again. Well, you can see, okay. If I hold it up like this, it basically, let's see if you can see it. Yeah, you can see down here. It basically is kind of like a roll of film. It's got the same type of stuff as a 35 millimeter roll of film going across here, and that's how you track it through the thing. And it's basically layers of insulating plastic and gold metallization, and then different things. I remember when we were working, when the students were working with deck, there were something like 200 different process steps just to make this tab tape. So you start out with a piece of, I think it was polyester film, and then you'd lay gold on, then you put tin on, and then you take something off, and then you put something on. And if you look at this thing, I'll pass it so you can look at that again, but you look at this, there's 500 wires, connections going back and forth. And that particular carrier that you got there is basically what Intel would sell you if you wanted to put a Pentium onto a printed circuit board. So here's a printed circuit board, and let's say I wanted to bond this to the printed circuit board. The printed circuit board would have connections. The inner lead bonds are made around the chip, and these are called the outer lead bonds out here. And they will basically cut through, they will actually come down and bond all the way out here, all these outer lead bonds. See, if you look at the real ones, you can see the very fine wires in here. And then they'll slice it off, and everything around the outside of that is just trash. You throw it away. This is just a chip carrier. The inner lead bonds have already been made by Intel, and if you want to put your chip onto your circuit board, you make the outer lead bonds, and Intel will tell you how to do that. And you basically come down with a tungsten electrode that heats up the thing, and it's got, some of these things are tinned, and you make a bond between the gold and the tin. It's a hot bond. You actually are making a gold tin alloy typically. So it's not a cold weld so far as that goes. But if you look at that, there's lots of detail in there. Each one of those little tab tapes goes for about 50 bucks a piece. So it's not a cheap bonding process, but you can get lots of IOs, which is one of the purposes. Okay. Well, tab bonding, it turns out for tab, you can get to about, wire bonding, we were a separation of 0.007. For tab, it's about 0.004. And if I've got 1.6 inches around and I've got 4/1000ths of an inch, that's basically about 2/1000ths of an inch line width of the wire and about 2,000 inch spacing in between the wires. Then I get about 400 IOs. And I don't use up all that extra real estate on the silicon chip. Well, that's where we were about 1995. But then, essentially, around 2000, actually before 2000, people were using flip chip before that. People went to flip chip. This is a flip chip. And in flip chip, you don't rely on perimeter bonding. You basically put your chip on this side. This is for a relatively small chip. Up here, I'll pass this one around. And then, I've got another one over here I can play with. You put your chip on this side, but again, this alumina ceramic is got all kinds of multi-layers in here with wiring that goes through it. And so on one side you put your chip, and the other side you have your connectors all the way, array of dots, right, on here. And then you put a little solder bump on each one of those. And these things can get pretty big. In fact, if I look inside my Macintosh desktop, or actually probably if I looked inside a laptop, I gave that one away to my son. So I would see this type of, sometimes called ball grid array bonding, BGA. Okay, it says ETA down here. But here's your chip. And then on the back side, you have these little pads, and you put some little solder balls, in this case, 0.7 of a millimeter in diameter. That's about 28 thousandths of an inch, right? And then you'll have a pad down here that you want to bond to. And that, actually, this isn't the pad. I don't have any of those on these. But, and I can bond that directly to a printed circuit board. In cross-section, it looks like this. Here's my integrated circuit. There's my chip. I have all these, in this case, well, I can either do it directly on the integrated circuit. In some cases, this is the piece of silicon rather than a piece of aluminum oxide. And I actually have vias going through the silicon to make the electrical connection. I have these little solder balls, and here's my substrate. So that's called ball grid array or flip chip or C4. The failure rates are all, well, not classified, but they're all proprietary to the companies. But typically the failure rates are now down less than 10%. Actually, probably less than 5%. In many, a really good outfit is probably down % or 2. But you do have to do burn-in. But it has to be down to something like that because you're going to pay $200 for your, your Pentium chip. Okay, and so you screw it up, and you just screwed up $200, and it's not easy to recover from it.
Now, what's the chip that is manufactured? Like this, the computer manufacturer that you ever sell, what's their failure rate to put the chip onto the board?
Well, I was kind of to make the silicon chips. I mean, it used to be to make a silicon chip, you get like 25% yield off the silicon wafer. Only one chip in 4 or something. They're up well above probably 99% now. Okay, they have made, that's how Intel got to be so big. In terms of making these bonds, interlead and outer lead bonds, and you're talking about 400 interlead bonds and 400 outer lead bonds, you're talking roughly 1,000 bonds. That's probably in the 1 or 2% range. So it's kind of combined of interlead bonds and outer lead bonds is down in a couple of %. So if it's Toshiba or anybody else, they're using the same type of equipment as Intel or anybody else, and they work with them. You want your customer to be successful bonding your chip. Okay. There are certain advantages. I mean, so the reliability rate really is much better than Six Sigma if you talk about individual bonds. Okay. Six Sigma is 3 parts per million failure rate, and if you've got 1,000 chips, that would be, and any failure. So you'd fail 3 out of 1,000 if you were at 3 or 4 ppm Six Sigma. So you got it. That's actually probably where some of the reasons they chose Six Sigma, so that you're down to a couple of % failure rates. But it is just a couple of % failure rates. But it's also the rest of the whole circuit board. Or to give you another idea, these are. I was not going to go into this. This basically. There's different levels of chip connection. Well, let me back up and tell you what C4 is. C4 is this is controlled collapse chip connection. In the military, 3C cubed is command, control, and communications, right? And then C cubed I, right? For integration, it's I for integration or something, anyway. Well, C4 was invented, this ball bonding on the area, or ball grid array, was actually invented by IBM, I think in the late 60s. IBM could this is when they had lots of money. They could kind of see they needed to go this way, and they invented this stuff, but it never started to catch on in the 1980s when chips kind of caught up to this need for higher I/O. And IBM calls it C4. Other people call it ball grid array. Other people call it flip chip because you basically, the silicon chip gets turned upside down, gets turned on its head. But to get back to your question of what's the reliability, they talk about 4 levels of interconnect technology. The zero level of interconnect technology is on the silicon chip. Okay, so if I'm making bonds on the chip by vapor deposition and laying down aluminum wires on top of silicon, that's zero level. The first level is this kind of bonding from the chip to some circuit board. The second, so there's zero level, first level, what they call the second level. Second level is bonding from the circuit board to another part of the circuit board. And then the third level, which is actually the fourth one up, is connecting from this circuit board into a bunch of other circuit boards, okay, into a system. So I've got a rack with a bunch of circuit boards, and you have connectors that each circuit board plugs into, right? On the back of one of these circuit boards, there should be, this isn't a whole circuit board though, or maybe not, maybe this is. Anyway, there's some plug connector that everything connects into. So if you're talking about microelectronics, there's four levels. There's on the chip, from the chip to the circuit board, within the circuit board, and then from circuit board to other circuit boards. And I guess you can talk about connecting from big racks to somewhere else, which now you're starting to get into, you know, Boston Edison or something, or communications, Comcast or something, communicating other ways. So there's all kinds of different levels of connection, and I've been talking about how do you not what's happening on the chip, but the first level where you're going from the chip to the circuit board. And it used to be that you actually, in some of those other packages, you would package the whole thing into aluminum substrate, and you would just buy the aluminum substrate. But because people are worried about what they call the real estate on the circuit board, they actually are putting the chips directly onto the circuit board, which may have been your question. And that's why Intel sells you the chip unencapsulated, so that you can put it directly onto your circuit board, so that you can save real estate and you don't have all this extra level of connection in there, because every set of connections means another potential failure location. Well, some circuit boards, well, the other circuit boards tend to be done by soldering, and we're going to talk about soldering a little bit later, but I brought this because I had a student working up at what's it? Teradyne. Teradyne makes semiconductor test equipment, but it turns out they also make big circuit boards. This is one of the smaller ones they make up in New Hampshire. The bigger ones are about twice this size. And essentially, this is a circuit board that goes into, let's say you've got a Verizon distribution center where circuits are coming in and then it distributes it out. So if I've got Comcast, Comcast is going to have some sort of junction boxes that redistribute everything in the neighborhood. So all the signals come in on some high-speed line, and then it's got to all be redistributed somewhere. This is the type of circuit board, or Verizon, or telephone companies are going to have boards this size. It starts out as sheets of plastic that have copper on them, and you etch away the copper. You actually do a photolithography. You put a little polymer layer on, and then you cure the polymer layer with ultraviolet light or whatever. And then you get rid of the polymer that wasn't cured, and so you've made a pattern on here, and then you etch away the copper through the polymer acts as a paint that keeps the etchant from etching the copper where you want to leave the copper, and the copper just gets etched away on this thing. So I don't think you can cut yourself on that one, but if you want to, you can make noise with it. It makes really good noise. So they take those and they laminate them together on something like this. And I won't hand around the whole big one. Here are a couple of pieces from different circuit boards. These have up to 40 different sheets in there. You got the thinner one, they got the thicker one, has more sheets. But typically 20 to 30 to 40 sheets like that are all laminated together in a big press, and there are joints in between. So this whole thing going through there is just like that little aluminum oxide chip carrier, but on a much bigger scale. Only here I've got copper and tin in between in the aluminum chip carrier, because I'm I'm doing this on a ceramic substrate that gets fired at very high temperatures in a furnace, they have to use tungsten as the via interconnects. So if you want to look at, there is it's sort of an amazing structure, and you probably, I don't have a good picture of it right here, but you've probably seen some of the cross sections through some of this is through a solder bump. You'll have you have to passivate the surface where you don't want the solder bump to go. You coat with the resist, and this can be for either on the silicon chip or this can be on the big circuit board. So we're talking about doing it this size or doing it that size, right? It's just different equipment. And you come in here and you may plate with copper, and then you put the lead tin on top of that, and then you strip the resist. You might, well actually, no, I'm sorry, they're going here. Here to sputtering titanium copper, and the reason they do titanium is so you don't get diffusion in there. Coat with resist, pattern for the bump, plate the copper, and then the lead tin, make this, strip it, and then you reflow it, you just melt it, and it will naturally, we'll talk later about why it forms a nice spherical ball. Okay? So that's how you make a solder bump. If that solder bump, you're asking about reliability, it turns out one of the nice things about C4 is it's self-aligning on this, on the tab bonding or the wire bonding. You got to get everything aligned pretty well, but they typically have like 50x microscopes, and someone checks it before they turn the machine, tell the machine to go to work to make sure that everything's aligned. And they actually have vision systems and little reticules or little fiducial marks on the chip that the vision system looks for those to align everything. So they don't usually have alignment problems much anymore because they used to lose a lot of money when they had misalignment. But they've taken care of it with expensive systems to make sure everything lines up. One of the nice things about flip chip, as opposed to perimeter bonding, is it's automatically aligning. Once you take these solder balls and you bring them in here, and let's say this thing's off center, you see the pad is off center on the pad. If you actually melt it and it wets the surface, there'll be a surface tension that essentially brings us a shear force, bringing this thing back into alignment. So it turns out that you can make 1,000 bonds or 10,000 bonds, and things work pretty well. Now, one of the problems is if your chips get really big, you really can't use that whole area because the coefficient of thermal expansion out of the outer periphery of that big chip, if it's 1 inch on the side, you've got too much thermal expansion and you may shear these things in service. But in fact, I didn't make copies of it, but if I looked in this book, they actually have some pictures of some things. I probably should be a little bit careful about how I say this because about 10 years ago I had to sign a confidentiality. But since I'm now reading it in this book, so maybe I don't have to worry. Confidential. But basically, the aspect ratio, the height of these things, well, it's not too hard to figure out. But at the time that I had a student working on it with one of these companies, it was kind of a big revelation to them. If you make these things taller, then you can absorb more shear, right? It's not too hard to figure out. But that was a big revelation, and I had to sign a big confidentiality when the company discovered that, and they didn't want me spilling the beans to everyone else. So it turns out they've learned a lot of things about how to do this, and they actually can start getting 1,000 I/O circuits on these things. But they're still running into lots of problems. Not that there's a huge number of problems, but they still have problems. Okay, these are, if I have a quad flat pack, and this is a J connection, and this is a gull wing connection, it's just a question of whether the tabs, these are the tabs coming out of some of these other packages, and I want to solder them to a circuit board like this. And it's just showing that when this is a soldering operation, we'll talk soldering another time, but this is a poor solder joint. The solder didn't wet well there. And then this one, that's a good solder joint, but and that's a good solder joint, but I've got some bad joints in here where the solder didn't flow around it. If things are going well, you probably can make 1,000 or 10,000 joints without any problems with the solder when you're talking about reliability. But look at this circuit board. You know, if I make one of these, I might have 5 or 6 bad joints. Even if it's 1,000 or 2,000, you know, only 1 out of 1,000 or 1 out of 2,000. And so they actually have vision systems that go through and try to measure, you know, whether you have good joints and whatnot when these things, when you flow all these. Typically, there will be a little bit of repair, and that type of repair rate might be in the 10%. You know, well, actually, virtually every board like this probably has to be repaired, but it's repairable on this surface. Actually, what my student was working on at the time was, how do you check this board? Where's the big sheet? The laminated sheet. When you etched away the copper, they were spending millions of dollars for vision systems to check every sheet to make sure that the lines either got etched well, that they didn't have overage, that they were going to get a short, or they didn't have an open. Because what are you going to do once you laminate it together? You can't repair it inside. So they had to do 100%. They were doing 100% inspection of these things, visual inspection of both sides. And it turns out each machine was $500,000 to do the visual inspection. And they were going to have to go out and buy 20 more machines. It was going to be a $10 million investment at this one plant. And basically he looked at, did you have to do both sides? This side, which is almost completely covered with metal, is called the ground plane side. This side is actual connection side. And it turns out this is the more critical one. This one, you don't have a lot of fine lines, okay? So they only had to do spot inspections of these, but they had to do 100% inspection of these, okay? It's just, but the costs go way up when you start getting as complex as all these things are. Well, the finer the line, obviously. From the etching process, it really is just fineness of the line. And so they already knew, but it really didn't matter about if I had this one versus its brother, which was slightly different. There weren't big variations. It was really how fine the lines get. Okay, and it's just because that photoresist you're putting down that paint. If it goes down and the paint slops over, basically, then you left too much copper there. If the paint peels back for some reason, then the photoresist peels back, then you eat away your connection. And then it was a question of the reliability of the vision system and everything else. It is sort of amazing that they can actually build something this complex and never have it work. But I can't tell you what the failure rate of these were, but the failure rate of the boards, and it wasn't hard for me to get. You know, I could have as many boards as I wanted because they had failures. And they would do failure analysis to find out what it was, but they had to cut it out. And that's why I could get this one. This was one of the boards they had to do a failure analysis on. I can't tell you because it's proprietary, but they had a substantial number. They had a lot of scrap, okay? And I can't give you a number, but it wasn't 1 or 2% scrap. It was substantially more. And they were working on it. I suspect now it's been 3 or 4 years, and the scrap rate may be down, you know, to a more acceptable level. But it's a pretty complex part and a lot of precision to it. And anyway, so I guess it's time. We'll finish up some of these things tomorrow and talk about electronic packaging a little more then. Okay.